So now let's generate several PowerFlow results using a time series PowerFlow computation. So GridCall has some functionalities to create a driver object to run a time series PowerFlow automatically, but we will take a slightly different approach since our function relies on the results for a single PowerFlow computation. So let's get started by creating a new notebook from scratch, and that notebook we can simply call it generate time series PowerFlow for the SMIB. So here we have more or less the same dependencies, so we have to import everything from pf to rec, and likewise we must import GridCall. And to work with time series PowerFlow, we will also need the well-known library pandas. So here, besides defining our OpenIPSL version, we are almost done. And then, as you might expect, we need to specify the same, more or less the same as we did for the single PowerFlow. So we need the data path here, and we would eventually need also the file handler and the PowerFlow option. So I will copy this where needed. But for the data path, let's run it. We are almost done. So let's now get some information about on which we will run the time series PowerFlow computation. So basically, if you check in the repo, you will find this zip file containing that when you unzip it, you'll find this CSV files. Each of this contains the information on an with a timestamp of 1 hour of the measurements of power consumption in different areas of the New York grid. So what we would like to do is to vary the consumption of the loads based on the trends that we observe with these PowerFlow measurements. So in order to do it, what we will do is to read those CSV files. So let's use one CSV file for varying the active power of our load and another one to vary the reactive power. So in this case, for the active power, we will read the CSV file under hourly basis for, let's say, New York City. And for the reactive power, let's do the same for instance hourly basis, the capital region. So then when we do this, let's have a look into the load P data frame, and we observe that the timestamps are contained in the column unnamed 0, and the load data it's in the column 0. So what we would like to do now is to first extract the timestamps. So the timestamps, we can get them from load P in column unnamed 0. And besides that, we would like to get values for the active power and the reactive power. How are we gonna do it? So first, the values are in the column 0, and we can access the values just by pointing to the actual NumPy arrays within the pandas data frame as follows. So then the main idea here is that we don't want to increase the load that much, but we would like to follow the profile. So to follow the profile, we will multiply the base case PowerFlow consumption by a number between 0 and 1. And the easiest way to do it is to divide these values by the maximum of that array. So let's copy and paste the same for Q. let's run this and let's have a look into pload values. So now we have an array, and that array has numbers between 0 and 1, and for Q is the same. So what we will do, I will repeat it once again, is to use this array as some sort of trend that when multiplied by the base case power flow P and Q will give us a change that follows the same pattern that was observed in New York City and the capital region during that particular day. Now let's do more or less the same that we did in the single case example. So we will create a GridCAD model from a pssc raw file, and what we have to do new here is that we have to format the profiles. So GridCAD has some arguments that are directly compatible with time series power flow, but we need to format them when we read a model from pssc. So how do we do it? So we will pass the timestamps, but we are not interested in knowing whether the exact timestamp that corresponds to each power flow. In this case, we only care about generating as many power flows as timestamps we have. So let's just pass this as follows, right? And actually this has to be the length of timestamps. So here our profiles will be we'll have 24. So each element within GridCAD will have 24 timestamps, or could store 24 values to run a time series power flow. Now let's change the values of the elements within GridCAD. So there are many ways to do it, but I like to do it using a for loop. So for each load that you find within the model, what we will do is to store the value that we want in the profile. So in the active power profile, what you would do is to take the base case power flow result and multiply it by the load value that we had defined here, this value that is between 0 and 1. And let's do the same for Q. Load Q multiplied by Q load values. And just to check that everything is correct, let's print the newly created load profile as follows. And let's copy and paste this to rewrite it for Q. So there is only one load in the system, and this is what we get. So these are the corresponding P and Qs for the loads. We will assume that the dispatch of the generator remains the same, and then the difference between active power, the difference in active power will be taken care of by the slack bus. Now we have already the profile within the grid model. Let's now go back to our single case power flow. Then what we need to do is to define a power flow object, power flow driver, in other words. So let's do it here again. And then we need to run the time series power flow computation. So this could get tricky, but it's actually simpler as the code suggests. So we would have an outer for loop that iterates throughout the timestamps. So for the number of timestamps in the time profile of the grid. So here, if we were interested in the timestamp by itself, then we would be using this second part of the tuple that we are creating with the enumerated method. But for the time being, we're just concerned about changing the power flows. Now we have to change the set point of the loads. So basically, we will run the time series power flow as a sequence of single power flows, where we will be changing the load information at each step according to what we have in the profile. So for load in grid.getLoads, what we will do is that load, the active power would be what we have in the profile at that particular timestamp, and the same for reactive power, right? So here at each time step, we will be changing the individual PQ from the, and we will assign the value of the profile. Then we can run the power flow, and using gridcal to rec, we can export that power flow result as a record. But we need to pass some additional arguments to what we had previously. So this is what we had previously, right? We will change export power flow results to false, because although we could export them as CSV files, but it would be a little bit annoying because there are many power flows. Then in power flow number, we would like to have the power flows a unique identifier, so it could be related to the time series step, that is NTS, but we will add one because Python is zero index to make this more intuitive. And the version of OpenIPSL is the same, but now we need to pass additional flags because we are actually doing a time series power flow computation. So here first we will say, we will indicate with a flag that this is a time series power flow by changing is time series to true. And we will pass a name that is the name of the time series computation. So this will be in every record that we generate. So in our case, we can just name it as SMIB time series. And that's it. So let me just move this down so that we can and make this a little bit tinier. Yeah. So this is the code to run the time series power flows. So let's, as we did previously, let's have a look into our PF data subfolder. We have only the base case power flow information. Let's run it now. And we should observe in a minute that this will get updated and will be populated with 24 power flows, one for each hour within the data that we got. So here in our model, we need to refresh it. So let's refresh it. And when we refresh it, we go to the base case. And in the power flow element, we can see that all of the different power flows coming from that time series power flow computation have been automatically linked to the model. So if we want to work, for example, with the time series power flow number 20, then we replace it here. We check our model. And we simulate it. And what we will observe here is that once the simulation is completed, this plot will get updated with the latest simulation results. And if the power flow is physically meaningful, we should observe a flat profile, as we do here. But now the voltages are closer to each other because this is a different power flow condition. So now to conclude, let's add some dynamics to the model. So basically we have these three-phase fault acting at 1 second. So let's simulate for 2 seconds and observe how the voltages in the system react. So the profile is the same up to 1 second, and then at t equals 1 we observe how the voltages go down, but when the fault is cleared they return to a steady state value. So that's it for this tutorial, and feel free to reach out in case you have questions or you have suggestions to our code. Thank you.